All right, so we're about to start our next moment distribution example. So we're going to jump right into it. In this example, we want to do the following. We want to use moment distribution to compute the end span moments. Okay. Unlike the other examples we've done, I'm not going to have us compute the external support reactions or draw the shear moment diagram for this problem. We could, but we're just going to just get the end span moments for this example. So let's take a look at the beam we have. We're going to have a fixed connection at A, and here's our beam. On the opposite side, we have another fixed connection, and then we got a couple of rollers kind of in the span here. And we have a uniform distributed load of 4 KLF. And then this is going to be support B, support C, and then D is on the opposite side. And then we need some dimension lines here. So our dimension lines are going to be 10 feet for span AB, 18 feet for span BC, and 15 feet for span CD. So the first thing I always like to recognize is what's the degree of static indeterminacy. So we have one long continuous member, n equals 1. Our reactions, we've got 1, 2, 3, 4, 5, 6, 7, 8 reactions. So 3n equals 3. And so this should be indeterminate. So we have a degree of indeterminacy of 5th degree, indeterminate to the 5th degree. So pretty indeterminate. So the next thing we want to do is kind of put together our stiffnesses. I forgot to mention EI is constant. EI is constant for the entire beam. Okay. So that should be given. All right, so let's get the stiffnesses. We're going to have stiffness in span AB is 4 EI over 10 feet, or we could use relative stiffness. Remember, we've mentioned before, if EI is constant for the entire system, we could use relative stiffness. But we don't have to. Okay, we have KBC, which is 4 EI over 18 feet, and then we have KCD, which is 4 EI over 15 feet. Okay, then we can use these. Remember, the whole purpose of getting these stiffnesses really is to then calculate the distribution factors. So how many distribution factors are there per span? Well, there's always 2 distribution factors per span. So we're going to have a distribution factor called AB, all right? And that's going to be KAB divided by KAB plus infinity. So that should be a distribution factor of 0. And then we're going to have a distribution factor for BA. So we're looking at the joint B, but we're still in the span AB. So that's KAB divided by KAB plus KBC. Okay, so when we punch this through, we get 4 EI over 10 feet divided by 4 EI over 10 plus 4 EI over 18 feet. Okay, so one thing I want to point out here, let me make my division bar look a little nicer. I don't know if that looks much nicer or not, but one thing we want to point out here is that because EI is constant, all the EIs will cancel. So that's why we could have just used relative stiffness, because notice, actually, in fact, the 4 EIs all cancel. So what you're really left with is like relative stiffness terms. So when you punch this through, you should get 0.64 0.29 as that distribution factor. Then we're going to calculate the distribution factor for BC. So now we're in span BC. So we got KBC in that numerator divided by what's connected at B. Well, span AB is providing some stiffness. And then, of course, still span BC is providing some stiffness. So, canceling out the 4 EIs again, we could look at this in terms of relative stiffness as 1 over 18 feet divided by 1 over 10 feet plus 1 over 18 feet. And that ends up equaling 0.3571. So one thing I'd like to note, hopefully get you to recognize, you may have recognized this in a previous video, even though I didn't explicitly say it, the sum of the distribution factors at a particular point should be 1, okay? Should be 1. So that's one way to always kind of check yourself. Now we can get the distribution factor for CB. So we're still in span BC. So our numerator is KBC. And then what's connected at C? Well, KBC is contributing stiffness to joint C. And then KCD is contributing stiffness to joint C as well. So we would have 1 over 18 if we're looking at relative stiffness divided by 1 over 18 plus 1 over 15. And when you punch this through, you get 0.4545. And then the last distribution factor, actually almost the last distribution factor, is CD. So we're still looking at joint at the roller at C, but we're in span CD. So we would have KCD divided by KBC plus KCD. If you keep in mind what I had just said, the sum of the distribution factors at a particular point should equal 1, which means that we should be able to calculate a value of 0.5455 for distribution factor CD, but punch it through anyway and make sure you get that. And you notice that these two add together to get 1. Okay, and then now our last distribution factor is going to be the distribution factor for DC, which should be 0 because we have KCD over KCD plus infinity due to the fixed connection at D, so that's 0. All right, so the other things we need to keep in mind is FEMs, the fixed end moments in A, B, and CD are all 0 because you don't have any applied loading on span AB or CD. So we do have fixed end moments in span BC, in that kind of middle span. So FEM BC is going to be negative WL squared over 12, all right? And when you punch that through, let's see what we get. We get 4 KLF times 18 squared over 12. So I get negative 108 kip feet. And then the fixed end moment on the other side of that span, CB, is just positive WL squared over 12. So that's positive 108 kip feet. Okay, so at this point, I like to make my table, my moment distribution table. So I'm gonna kind of come to the top of the next page. So what I recommend, I mentioned this in another video, make sure you have plenty of room to make your moment distribution table. And then I would do your calculations of the unbalanced moments and the carryovers on maybe another sheet of paper. So do all your calcs maybe on a separate sheet of paper and leave yourself plenty of room to organize your figure in your table. So I start my table, I always like to start my table with the beam itself. So here's my beam, there's A, there's D, and here is my roller at B, and then here is my roller at C. Then I got my distributed load for KLF, and we know EI is constant. It's constant for everything. So put my dimension lines here. Okay, so I like to use my beam figure to kind of shape up my table. So I just kind of project vertical lines down from these relevant dimension lines. This is just kind of a good way to be organized. I actually learned this organizational trick. It's not really a trick, but this organizational method from Dr. Sagi, who is the author of our steel design textbook, when I took Dr. Sagi for this course when I was in graduate school. So I like to go ahead and put in my K values. I'm just going to use K relative values just to make my life easier. So it's 1 over 10 feet, 1 over 18 feet, and 1 over 15 feet. And then I can put my distribution factors here. So we had a 0 here. We had a 0.6429. And then we had a 0.3571. And then we had a 0.4545. We had a 0.5455, and then we had 0 again. And again, notice that we mentioned earlier the sum of the distribution factors at a particular point right here should be equal to 1, okay? So keep that in mind. Same thing is happening here, equaling 1. All right, so next thing we're going to write in here is our fixed end moments, FEMs. And so we have 0 and 0. We have negative 108 and positive 108, and then 0 and 0. And out here I can put my units are kip feet. Okay, so so this is what we have so far. If you want, you can kind of put some horizontal lines here to kind of shape up this table. All right, so the first question we need to ask is, where do we have an unbalanced moment? Well, we have an unbalanced moment in 2 places. One spot is at point B, and the other spot is at point C. And we know that because we should have a moment, if we look infinitesimally to the left and infinitesimally to the right of a roller, of an interior roller, the moments should be equal in magnitude, opposite in direction, which is not the case here, right? We have 0 and 108. So, and then we have 108 and 0 on the other side. So we have unequal moments, unbalanced moments. So we could start at either joint B or joint C with our calculations. I'm going to start at joint B, but we could just as easily start at joint C. So I'm going to scroll down a little bit and give myself some room for further calculations if I need to expand that table. So we're going to have an unbalanced moment at B, and that equals 0 minus 108 kip feet, which clearly equals 108 kip feet, okay? And then what we do is we multiply this is negative right here. We multiply the negative of this unbalanced moment by each of our distribution factors, okay? So if you remember this from the previous video, we first say distribution factor BA times the negative of this unbalanced moment. So we say times positive 108 kip feet, and distribution factor BA was 0.6429 times 108 kip feet. And when we punch this through, we get about 69.4 kip feet. And then we're going to have distribution factor BC, because remember we're at B, times 108 times the same value, the negative of this value, kip feet. So this is 0.3571 times 108 kip feet, and we get a positive 38.6 kip feet, right? And then half of each of these moments are going to get sent to the adjacent supports. So then what we're going to say is our carryover factor is always 0.5. So we're going to say 0.5 of 69.4 kip feet is equal to 34.7 kip feet sent to A. So that's carried over to A. And then we're going to say 0.5 times 38.6 kip feet equals 19.3 kip feet. And that's sent to C, or carried over to C. So when I populate my table up here, here's what's going to happen. I'm going to have the 69.4 on this portion of the table because that's what's corresponding with the distribution factor of 0.6429. And then I'm going to have the 38.6 on this portion of the table because that was calculated from the 0.3571. And now this is balanced, and half of each of these values is sent to the adjacent support. So what was sent to A? Well, 34.7 was sent to A. And then what was sent over to C? Well, 19.3 was sent over to C. Okay, so B is balanced now, but what is still unbalanced? Well, C, not only is C unbalanced, but it's even more unbalanced now, okay? So now we're going to kind of repeat the same process, and we're going to say we have an unbalanced moment at C, and that equals 108 kip feet, and you have to add to it what you just sent over there, so plus 19.3 kip feet, which gives us a value of 127.3 kip feet, okay? And now we're going to take our distribution factors that we're utilizing at C, okay? So we're going to first look at the distribution factor that's infinitesimally to the left of C, which is CB, distribution factor CB, times the negative of this unbalanced moment, because we're trying to balance it now, so we need to negate that value. So minus 127.3 kip feet. So that distribution factor was 0.4545 times negative 127.3 kip feet. So I end up getting a negative 57.9 kip feet. And then on the infinitesimally to the right of C, I've got distribution factor CD times negative 127.3 kip feet. And this distribution factor was 0.5455 times negative 127.3 kip feet. So when this one gets punched through, I get negative 69.4 kip feet. And then we need to, remember, carry over 50% of each of these values to the adjacent supports. So we're going to carry over 0.5 times negative 57.9 kip feet. That ends up being basically negative 29 kip feet, and that's carried over to B. And then we're gonna say 0.5 times negative 69.4 kip feet. So that value is negative 34.7 kip feet carried over to D, okay? So let's populate our table now, all right? Let's populate this table. So what did we just do? We put into this a balancing effect. So infinitesimally to the left of C, we have negative 57.9. And then infinitesimally to the right of C, we calculated negative 69.4. So this is balanced now. And you can always make sure this is balanced by saying like, if I sum these moments, I get a number. And if I sum these moments, I should get the same number, but the opposite sign, okay? So therefore, you should be getting same magnitude of the sum of the moments on either side of the support, but opposite direction. One should be positive, one should be negative. So when we did our carryover calculation, what got sent over to B? Well, negative 29 kip feet got sent over to B, and then negative 34.7 got sent over to D. So my question now is, what is balanced and what is unbalanced at this stage? Well, we just balanced C. C should be fully balanced now. But when we had to perform those carryover calcs, we just created an imbalance at B now. So now B is out of balance again. What about A and what about D? Are those out of balance? Well, not really, because remember, A and D are fixed connections, and you can throw as much moment as you want at fixed connections, and it can absorb and resist all of that. So we don't need to worry about balancing moments at A and D because they're fixed, okay? So next thing we need to move to now is we need to move back to B, and we got to balance off this now unbalanced moment at B. So because this is the third example, and I've shown a lot of the detailed calculations, I'm going to kind of bullet point these next several calculations just to save a little bit of time. So we have an unbalanced moment at B, and this is equal to negative 29 kip feet. So when we distribute, we're going to distribute 0.6429 times positive 29 kip feet, and that's 18.64 kip feet. And then we're going to distribute 0.3571 times 29, positive 29 kip feet, and that's 10.36 kip feet. And then when we do our carryover calculation, we take half of each of those. So we would say 9.32 kip feet carry to A, and then 5.18 kip feet carry to C. And again, these two numbers came from taking a carryover factor, which is always 0.5 times each of these numbers. Okay, so I'm kind of, like I said, I'm kind of not explicitly saying everything anymore because I'm assuming y'all are getting more comfortable with this. So let's see, what do we need to put down next? We got 18.64 here. We got 10.36 here. That becomes balanced, and we carry over half of each of those values to the adjacent supports, 9.32, and then we have 5.18 carried over here. All right, so what's unbalanced now? Well, now C is out of balance, so we need to perform a similar calculation on C, unbalanced moment at C, and that equals the 5.18 kip feet. So let's distribute. Sorry, you may hear some racket going on in the background. We're just kind of shuffling some things around in one of our rooms. So we're going to distribute 0.4545 times negative 5.18 kip feet, and that's negative 2.35 kip feet. And then infinitesimally to the right of C, we've got 0.5455 of a distribution factor times negative 5.18 kip feet equals negative 2.83 kip feet. And then our carryover, we're going to take 50% of each of these values and carry them to the adjacent supports. So we're going to have negative 1.18 kip feet carry to B, and then negative 1.42 kip feet carry to D. Okay, so scrolling back up here, let's populate this table one more iteration. So we've got our negative 2.35 that we just calculated and negative 2.83 at C. This balances us off at C. And then what gets carried over to the adjacent supports? Well, negative 1.18 goes to B. And then, let's see, negative 1.42 goes to D. So what do we have now? Well, we just created another imbalance at B. So let's do this another iteration or two. Notice that our unbalanced moments are approaching zero. So I'm going to extend this table just a little bit farther because I'd like to converge to a smaller number than we did in our previous example. We had a bit of a if you remember the previous example, we had like a 6 kip foot discrepancy. I want to avoid that this time. So here we got another unbalanced moment at B. This was negative 1.18 kip feet. And so let's distribute. We're going to have 0.6429. That's a 4 here. Times the negative of that 1.18, so that's positive 1.18 kip feet. So I get positive 0.76 kip feet, and then I've got 0.3571 times 1.18 kip feet, which gives me a positive 0.42 kip feet. We are balanced now at B, but we still got to carry over. So we want to carry over 0.38 kip feet to A, and then we want to carry over 0.21 kip feet to C. Okay, so coming back up here, we're going to balance off our values at B. We got 0.76 and 0.42. So B is now balanced again, but we got to carry some things over. We're going to carry over 0.38 to A, and we're going to carry over 0.21 to C. Okay, so at this point, this may be a pretty good stopping point. I say that because if you look at the lack of balance, we have an imbalance at C of 0.21 kip feet. But think about it this way, it's 0.21 kip feet out of like 100 and something kip feet. So we're probably okay to stop now. We could do one more iteration if we wanted to. But, this is probably an okay stopping point. So I'm going to go ahead and terminate at this point just because this is such a small number out of like 100 or so kip feet around point C. Okay. So, but again, we could keep iterating as many times as we wanted to. In Excel, that would be fantastic. Hint, hint, wink, wink. So if you sum moments vertically, again, we're summing them vertically now. I'm going to punch this through. So at A, we got 34.7 plus 9.32 plus 0.38. So I get 44.4 kip feet at A, so that's the moment in AB. And then infinitesimally to the left of B, I'm going to have 69.4 plus 18.64 plus 0.76. So I get 88.8 infinitesimally to the left of B. Now, if I've done things correctly, I should get about the same number, if not the exact same number, infinitesimally to the right of B. So I'm going to say negative 108 plus 38.6 minus 29 plus 10.36 minus 1.18 plus 0.42. And sure enough, I get negative 88.8. So that really emphasizes B is balanced. And notice our last iteration was what balanced B. So let's look at C now. 108 plus 19.3 minus 57.9 plus 5.18 minus 2.35 plus 0.21. I get 72.4. 72.4. And then what's happening infinitesimally to the right of C? Well, we got negative 69.4 minus 2.83. So I get negative 72.2, okay? Negative 72.2. So that's pretty close to balanced. I mean, we're looking at a discrepancy of 0.2 kips out of 72. So we're in pretty good shape, okay? And what is that imbalance? Well, that's just this value right here, really. And then finally at support D, I've got negative 34.7 minus 1.42. So that gets me a value of negative 36.1. And all of these values have units of kip feet. These are moments. So if we want to make a summary based on what the problem asks for, then we have the end span moments are the following. We have MAB, which was 44.4 kip feet rotating. It was positive, so it's rotating clockwise. Okay, and then we have MBA, which was 88.8 kip feet, and that one was a negative value, which means it's rotating counterclockwise in the span, right? In the span. MBC was 88.8 kip feet. That one was a positive value. Oh, I'm sorry. I looked at these backwards. Here. MBA, I believe, was the positive value. I'm sorry. So that's clockwise. And then MBC was the negative value. So that one's counterclockwise. We're good. We're good now. I just looked at my notes backwards. And then we have MCB. MCB was, what did we get for that? We got a positive 72.4. So we're going to say 72.4 kip feet going clockwise. And then MCD was 72.2 kip feet going, it was negative, so it's going counterclockwise. And then MDC, that fixed connection, was, I believe, 36.1 kip feet. And it was a negative, so it's going counterclockwise. So I want to emphasize here, remember, these are moments in the spans at each end of the span. So if we were to look at a free body diagram of these rollers, for example, the moments would be in the opposite direction, looking from the perspective of the rollers. Okay, and remember, positive is clockwise, negative is counterclockwise in moment distribution calculations. So if we wanted to use method of sections to get the external support reactions and draw the shear moment diagrams, we absolutely could, but we're just not going to in this particular example. Another thing I want to make sure we make a note of, okay? So under this note, if we deal with a problem with EI not constant, this will affect the distribution factor values. Okay, so remember, you're going to have a homework problem where you have EI is different in some different spans. So how does that come into play? Well, think of this. Where does EI come into play? Well, you use EI to calculate K, and then you use the K values to calculate the distribution factors. So if EI is different for different spans, you just build that into K and the distribution factors at the beginning of the process, and that's how you account for a non-constant EI. So there's really no trick behind that, or nothing that you really need to worry about behind that other than build it into K and the distribution factors at the very beginning. Okay, thank you.